In this video, we'll be looking at problems from 16.2, Solving Exponential Equations. Alright, remember our two-step process that we've used all year long with regards to solving special equations. Step 1, we isolate the function. That's the absolute value or the square root or the square. And then step 2, we undid the function with the inverse. Undo function. Typically it's been with the inverse. This time we're going to do one of two things. We could A, use the power rule of logs to undo our exponential. Reminder of our log rules. The third rule, the power rule, says that we take the log of something to a power, that power will come out in front. And that's what we're trying to do, is get that variable out of the exponent. So that'll be very helpful to us here. Or we can set the bases equal to each other. That's not mentioned a great deal in this section, but it's often useful. And I'll show an example of both of those. Alright. Here we're looking at problem number 7. It says use common logs to solve the equation 6 to the 3x minus 9 minus 12 equals negative 7. Well, the common log is log base 10. When you see, if it just simply says log, it's an implied log base 10 because we're a base 10 number system. This is called the common log. If it says ln, that is log base c. That's the natural log. That number e is the irrational number, 2.7 approximately. Goes on and on forever. Any other log will designate what it is. It'll be log base some constant here. Alright, so we have the equation 6 to the 3x minus 9 minus 12 equals negative 7. Well, the first thing we're going to do is isolate our function. That is, isolate the exponential. The base to whatever power the variable is going to be in the exponent. That's what makes it an exponential. In this case, we're isolating green circle. What will we do? Well, we'll add 12 to both sides. When we do, we get green circle. And green circle is 6 to the 3x minus 9. And on the right hand side we'll have 5. At this time we're going to use that power rule, rule 3. I'm going to take the log of both sides. You can take any log that you would like. They will all work. In this case it'd actually be very effective to take log base 6 because we would end up with canceling out the 6 altogether, but it said use the common log, so we will. Again, that's a implied base 10 there. Whatever we do to one side, we do to the other. Now, I'm going to come over here with it. Change color so we don't get confused with what I've written above. When I take the log of the left side, the exponent comes out. So we have the binomial 3x minus 9 out in front, and times log of 6. From the left hand side here to this statement, we have brought the exponent out in front. That is, again, our power rule. The log of something to a power, the power comes out in front. The right hand side we'll leave as log 5. And we're pretty much done at this point. Log 6 is a number. Log 5 is a number. So this is a standard equation in one variable we've been solving for a long time. I could distribute this log 6 over this parentheses, but it'll just add an additional step. At this point, I'm going to divide by that on both sides. Just think of it as it's a number. In a second, we'll use our calculator to evaluate it. This cancels, leaving 3x minus 9 on the left-hand side. We have log base 5 over log base 6. On the right-hand side, now we'll add 9 to both sides, yielding 3x equals log base 5 over log base 6 plus 9. Then we'll divide by 3. X is equal to, you can divide both of these terms by 3 or the whole side. Divide both of them by 3 would be this, log base 5 of 3 times log base 6. And then 9 divided by 3 is 3. And at this point, you could use your calculator to evaluate this. Just simply go into the calculator and you'll find it's approximately some value. Let's take a look at what that would be. We could use log base A, but in this case we're using the natural log, so we can just simply type log. Log of 5 divided by 3 times log 6, getting out of our denominator, minus, plus 3. And we see that's approximately 3.299, and the problem said round, give the exact solution, this is the exact solution here, and an approximate solution to 3 decimal places. So our approximate solution would be 3.299. Again, this is the exact solution, just like we might leave it as square root of 3, and our approximate is 3.299. Alright, next. We're looking at number 10. Yours might be exactly the same, but it should be similar. We have e to the power of the fraction 2x minus 1 divided by 3 equals 270. So in this case, since our base is e, we're going to use the natural log. This will eliminate e altogether. Again, we could use any log we want, but if you use the same log that is the base, you're going to be able to employ another important rule for us, the 1 rule. Log base b of b is equal to 1. Another way to say that is b to the first power is b. So here we go. Step 1, isolate the exponential. That's done. We have the base to some power by itself, and now we're going to employ our power rule, rule 3, taking the ln of both sides. Ln of e to this particular power, 2x minus 1 divided 3, equals ln of 270. Now rule 3 says we'll bring that exponent out in front. We have 2x minus 1 over 3 times ln of e equals ln of 270. But recall, ln is log base e. ln is log base e. It's the natural log. So I'm going to you don't have to do this, but I'm going to rewrite it right here so we can clearly see what's going on. ln is log base e of e. Well, the 1 rule says if the base and what we're evaluating the log of is the same, it's 1, because anything to the first power is at anything. So at this point, log base e of e, that's 1. 1. And 1 times anything is that anything. So on the left-hand side, we have 2x minus 1 over 3. The right-hand side, we have ln of 270. Again, this is just some number. E to some power would be 270. That's what this expression is saying? Well, when we have a fraction, we can multiply by the denominator. Multiplying by the denominator on both sides yields 2x minus 1 is equal to 3 times ln of 270. Adding 1 to both sides yields 2x equals 3 times ln of 270 plus 1. And dividing by 2, x is approximately 3 times ln of 270 plus 1 over 2. And I could break that up. This is not approximately, this is exactly. And at this point you can use your calculator to find what that number is exactly. One last one, number 9. Alright, in number 9 I'm going to show a different method. Recall in the beginning I said there's, after we undo the function, we can use the power rule. That will pretty much always be effective. But occasionally we'll have a situation where we can set the bases equal to each other, and we can capitalize on what's called the one-to-one rule of exponentials. And that basically says this: if you have a to some power b and then a to some power c, it doesn't look like much of an a there. If these bases are the same, then the exponents must be the same. If this, then this, b is equal to c. And I think that makes sense. This is true because the exponentials are a one-to-one function. Alright, so we'll use that in this case. So in this case we have 4 to the power of 5x plus 3 is equal to 8. Again, you could use logs, take the log of both sides and get that out of the exponent. I'm showing a different strategy here. 4 is the same as 2 squared. So now I can take that 2 and put it in using the power rule of exponentials, run it right up there in the exponent. 8 is 2 cubed. So now we've got our situation. We have the bases are equal to each other. Since the bases are equal to each other, it must be true the exponents are equal to each other. I can now set both exponents equal. 2 times 5x plus 3 is equal to 3. I could distribute this 2, or I could simply divide by 2 on both sides. This time I'm going to distribute it. 2 is a very easy number to distribute. Subtracting 6 on both sides, I get that 10x is equal to a negative 3. And then dividing by 10, I get x is negative 3 over 10. We should take this negative 3 over 10 and substitute it back in, but it's going to work indeed. That concludes this video.